Welcome back. This is our final video, other methods of proofs that don't quite fit the previous categories. Okay, let's take a look at what they are. How to prove that two statements are equivalent. To prove that P is equivalent to Q, or P if and only if Q, remember that means that you have two implications. P implies Q is true and its converse is true. So prove both directions. Sometimes you will hear your lecturer say, prove that P implies Q and Q implies P. So for instance, if you want to prove this statement, let n be a natural number, prove that n squared is even if and only if n is even. It means that you need to prove that n squared is even implies n is even. I think we've done something like this in a previous video. And don't forget to prove that n is even, so start with that as an assumption, right? Implies n squared is even. So assume this implies that, and assume that implies this. Prove both directions. Okay, I'm not going to write down the proofs. You can try and write it down yourself. How to prove that two sets are equal? To show that two sets are equal, we show that one is contained in the other one. So prove that A is equal to B for two sets A and B. Prove that A is a subset of B and B is a subset of A. So here we have that A subset of B means that we assume X is in A, we show that X is in B. It's proving an implication, right? And B is contained in A means that we assume X is in B and we show that X is in A. Again, proving another implication. So this is quite similar to proving equivalence, right? In some sense. We're now proving that X is in A if and only if X is in B, right? So now let's take a look at this example and we demonstrate what we mean by that. We're going to show that these two sets are equal. 15n plus 3, where n is an integer, that's set A, and set B, 15k minus 237, again k is an integer, they are indeed equal. So, remember our lesson from writing mathematics. State your intention, keep the reader informed. First, we show that A is contained in B. Okay, let's pick a letter, M, B and A, right? So there exists, to be a member of A, there must be an N such that, this is an integer, such that that member of A is equal to 15n plus 3. Okay, so that's what it means for M to be in A. Now we want to show that M is in B. So we want to show that for another integer, M is equal to 15 times that integer minus 237. Okay, so let's see. Note that M, which is 15n plus 3, is equal to, okay, so here we need to do some arithmetic. 15 times n plus 16, right, minus 237. Okay, you're going to check the arithmetic by yourself. I have done this before I wrote this proof, and this and that I have checked that it's equal, but please check it by yourself. All right, and that actually shows that M is in B, right? Because there's an integer, in this case n plus 16, such that M can be written as 15 times K minus 237. Okay, and we're done with the first one. Now we show that B is contained in A. Should we use M again, or we can choose another letter? What should we choose? Let's say L. L is in B, right? So there exists K in Z such that L can be written as 15 times K minus 237. Now we want to show that L is in A. Okay? So we have that L, which is 15k minus 237, is equal to 15. Again, do this computation yourself, times k minus 16 plus 3. Okay. Alrighty, so that shows that L is in A, right? Because anything in A can be expressed as 15 times an integer plus 3. So we've shown that A is in B and B is contained in A. So we conclude that A is equal to B. And we are done. Well, you can actually improve this proof a little bit, right? So I'm proofreading my my work right now. Maybe it's better to actually say here that we have shown that A is contained in B, and over here also you can say that we have shown that B is contained in A, and that's more clear that A is equal to B, right? Okay. Sometimes people omit it, but I thought maybe this is nicer if we add a sentence or two there. Okay, that's a quick demonstration of proofreading. Okay, how to prove that two numbers are equal is actually the first one quite similar to proving two sets are equal. Just show that A is less than or equal to B and A is greater or equal to B. Or you can also show that their difference is equal to 0. A useful application of this is to show that two functions are equal. Okay, so to show that two functions are equal, we show that fx equal g of x, the functions are f and g, for all x in, let's say they're from R to R, right? Let me just say for all x. I think we are fine for now. Okay. Okay, we show that fx equal gx for all x. So you can, for instance, show for all x in x, so for all x, that fx is less than or equal to gx and fx is greater or equal to gx. Or you can also show that for all x, fx minus gx is equal to 0. All right. Okay, our final thing here is proving uniqueness. How do we prove uniqueness? Well, assume that there are two of them, or once you find one, assume there's another one, and show that both objects are the same. I'm going to demonstrate this with an example. Let A and B be real numbers with A not 0. Show that the solution to the equation ax plus b equals to 0 is unique. Okay. Proof. So we're going to assume that there are two solutions to ax plus b equals 0. Let's call them x1 and x2. That there exists x1 and x2 such that ax1 plus b equals 0, meaning that x1 is a solution to that equation, and similarly ax2 plus b is also equal to 0 because x2 is also a solution, right? So what we're writing here is saying that there are two solutions to ax plus b equals 0. What we want to show, that we want to show uniqueness, so we want to show that x1 is equal to x2. Okay, let's see. From ax2 plus b equals 0, we have that b is equal to minus ax2, right? And then we substitute this to ax1 plus b equals 0. We get what? ax1 plus, we substitute with a minus a x2 equals 0. And this implies that ax1 is equal to ax2. All right, so we are now in this situation, right? That we have ax1 equal ax2. But remember what our assumption is? A is not 0, so we can divide through this inequality by a. This equation by a, excuse me. So since it's actually equality, since a is not equal to 0, we have that x1 is equal to x2, right? And that's what we want to prove, and we are done. Okay, or you can write the conclusion maybe before you write your final QED sign. We conclude that ax plus b equals 0 has a unique solution. Okay, and that completes the proof. So that's the end of this video and the end of our series. I hope this has been useful for you, and enjoy proving some mathematical statements by yourself. Bye!